First things first. What are they, man? And then I have, well, I could do it on this one too, right? Anyways, let's do this. What was I saying? Here? No. So here. What did I do last time? I think, what the heck? No, maybe. What? nothing here. I don't know about her. Let me actually just should be the other one, I think. Quotations. Let's go. No, oh my opinion. So tall. I know. Jesus. No, that's it. You know, might be hard to be honest. Maybe that's her. I think that's her. I guess I could go here and see if I can. This is not in your box. No, she doesn't see me. More of this. Oh. Oh, nice. Yes. Yes. It's time. Ready to go to perfection. No. Alright, Willis. I think that's. I think that's. I think that's. Yeah. There's really nothing else. Right? Let me think about it. Anyways, yep. Yup. Okay. Okay. Alright, where to, let's go, yup, yup, yup. Huh, interesting. Slides down, what does all mean? Seriously? Mm, Cool. Okay, and not sure. don't know. Yeah, we'll see. Yeah, right. Um, yeah. Um, No. Yup. 199. What? 99. Where are you? Where are you? No. Huh? Well, that's quite strange, isn't it? Anyways, it should be 2020 winner. So we should look at this one. Seriously? Why? What the heck? Hmm? What the heck? Hmm? Hmm? Why is it not here? That's so strange. I don't know what we're using. That's so strange. Whatever. Anyways. Oh no. Oh no. Wait, what? And um, just maybe we were supposed to use something else. No. I don't remember what it was. Master. Name counts. Class mail archive. Just announcements. Beep, boop. Files menu. Mm. Oh, and we need to. No, it's still not here. That's what it was actually. Um, 182. Should be here. No, it's not. Oh, there you go. So strange. Very strange. Huh. Why not? That's so strange. Nice. Nice. Very nice. Um, mm, yeah. Mm-hmm. Okay. What else? M122. Oh, I did? Oh, yeah, I did. What the heck? What you did? Just like, I don't remember this at all. Okay. What is this with? Nice. And maybe psychology, right? Like that would make kind of sense. 780. This one. I can't access. I can't access anymore. Why? Freaking jerks. Psychology. Nice. Okay. Very nice. Cool. Is there anything else? I don't know. I don't think so. Oh yeah, I did want to try to get the other one. Syllabus, what is? No. What about no, go back. What's the code again? I think where did I go? Was that the dashboard? Yeah. Mm-hmm. Done. Oh, okay. I think I have it here actually. I sure can. No. Why are all my classes listed here? It's kind of strange. Well, that's kind of strange, isn't it? I do have not access to view if it's my course. What the heck? Oof. Okay. Strange. Okay, hold on, guys. We're back. We're back. No. Wait, wasn't this one? We're trying to write it. No. Where the heck is it? Oh, maybe he. What the heck? go. Yeah, that's fine. That's pretty good, I think. Okay, and yeah, let's just take it from there, I guess. I'll be back. I'll be back in a minute. I have to eat. Yeah. Mm, yeah, that's a little better, I think. You have no clue. Where was it? Yeah. Yeah. Maybe. heck? Why? Okay, bye guys. Let's get done. Right there. Yes. Um. Okay, hold on. What's left still to do? Can I study now or no? No, maybe I wanted to see. Where's the thing at? heck? Oh, wait. Not her.
As a series of chemical reactions that take place inside our body. Textbooks define metabolism, a topic in biochemistry, chemical reactions that take place inside of our bodies to sustain life. Now, this is a pretty broad definition of metabolism. So in this video, I really want to break this definition down to a more workable understanding of what metabolism really is. So first, I'm going to introduce another arrow in this diagram like this and say that really the requirements of life, let's say in a human being, such as, maintaining a constant internal temperature, reproducing, growing, and all that jazz, all of that ultimately boils down to the body's ability to utilize 4 essential biomolecules. And these 4 essential biomolecules, or as they're sometimes known as macromolecules, are proteins, fats, carbohydrates or carbs, and nucleic acids like DNA and RNA. And ultimately, all of these biomolecules perform different life-sustaining reactions inside of all of the cells in our body to ultimately promote life. So as you can see, we've already begun to break down this definition of metabolism. Essentially, what we're saying here is that metabolism is really the study of how we're able to obtain these important biomolecules to sustain life. So how do we obtain these biomolecules? Now, the simple answer to this question is, of course, that we eat food to obtain all of these important biomolecules. But there's an important word of caution here, which is that since most food comes from living organisms like plants and animals, these plants and animals also contain an array of proteins, fats, carbohydrates, and nucleic acids, but not necessarily in the same flavor or configuration that our bodies would prefer. So what do our bodies do instead? Well, in our bodies, we go ahead and eat the food. It's a very large head there, but you get the idea. And in our bodies, we break down this food through a process called digestion into the component parts of all of these biomolecules. So what do I mean by component parts? Well, the smallest subunit of proteins is called an amino acid, and our body breaks down all the different types of proteins that we digest into individual amino acids. And the same pattern continues for the rest of the biomolecules. So in the case of fats, we're talking about fatty acids, which are the smallest subunits of fats. And then for carbohydrates, which are long chains of sugars, one of the most common subunits of carbohydrates that our body loves is called glucose. So I'll go ahead and write that here since you'll be seeing it a lot in the discussion of metabolism. And then finally, for nucleic acids, we're talking about nucleotides. So at this point, you're probably thinking, well, okay, I understand that our body can't use the same macromolecules found in food because maybe they're not in the right configuration, but how does breaking them down do anything for us? Now, the key here is to recognize that in our body, there's actually a delicate balance going on between the processes of breaking down molecules, such as in the process of digestion, and then taking these products and building them back up. So essentially, you can see all of these subunits or monomers as Lego pieces that we're essentially reconstructing to build the right configurations of proteins, fats, carbs, and nucleic acids that our body needs. So that's really the key idea here, which is that metabolism is a balance between breaking things down and building them back up in our body so that we can customize, so to say, what type of macromolecules that we create. And just to throw in some vocab words, biochemists call the process of breaking down molecules in our body catabolism, and a similar sounding word called anabolism is used to describe the process of building molecules back up. And the way I kind of like to remember this is looking at the first letter of each of these words. I think of C, I think of cutting molecules up into tiny pieces, so breaking them down. And then for anabolism, A, I think of as like the apex of like a building, for example. So we're building something up. Now, this seems all fine and elegant, but there's one more issue that we need to contend with, which is a consequence of having to balance breaking things down and building them back up. And that is that this process of building molecules back up requires energy, which I'm kind of indicating here by these yellow lightning bolt stars. So the question I want to answer in this last part of the video is, where does this energy come from? Now, the answer to this question is that, well, we also get this energy by eating food. So how does that work? So first, recall that the energy currency of the cell, and I'm going to go ahead and erase this just to give us some more space. The energy currency of our bodies is a molecule called ATP, or adenosine triphosphate. And this high energy molecule, as it's often referred to, when it is broken down into ADP, so it loses a phosphate group, it releases usable chemical energy that can fuel energy requiring processes in our body, such as the building up process of anabolism. Now, in order for this process to continue nonstop in our bodies, ADP must be regenerated into ADP. And that is where food comes in. So remember that we digest our food into all of these subunits, and some of these subunits, such as glucose and fatty acids mainly, but occasionally amino acids, so I'm going to put that in parentheses, can essentially be used as fuels in our body. So just like wood, for example, is a fuel for a burning fire, which produces heat. These fuels in our body can essentially be broken down even further to produce the energy that's necessary to convert ADP back into ATP, and thus allowing this cycle, which produces acids mainly, but a key comes in. So remember that we digest our food into all of these subunits, and some of these subunits, such as glucose and fatty acids mainly, but occasionally amino acids, so I'm going to put that in parentheses, can essentially be used as fuels in our body. So just like wood, for example, is a fuel for a burning fire, which produces heat, these fuels in our body can essentially be broken down even further to produce the energy that's necessary to convert ADP back into ATP, and thus allowing this cycle to continue. And just to throw in another vocabulary word that you'll probably see, this process of taking these fuels, which I've indicated with this asterisk, and breaking them down into usable energy is a process that's referred to as cellular respiration. And recall that because cellular respiration involves essentially be used as fuels in our body. So just like wood, for example, is a fuel for a burning fire, which produces heat, these fuels in our body can essentially be broken down even further to produce the energy that's necessary to convert ADP back into ATP, and thus allowing this cycle to continue. And just to throw in another vocabulary word that you'll probably see, this process of taking these fuels, which I've indicated with this asterisk, and breaking them down into usable energy is a process that's referred to as cellular respiration. And recall that because cellular respiration involves breaking down things even further, it's also a catabolic process. So it falls under this category of catabolism. And just to tie everything here together at the end, notice here that another way to interpret this cycling between ATP and ADP is to say that catabolism fuels anabolism. So what do I mean by this? Well, essentially, catabolism, such as the process of breaking things down and extracting energy through processes of cellular respiration, is coupled with this process of building things back up. And so in essence, one relies on the other. And as you can probably guess, these processes are really tightly regulated in our bodies because obviously you wouldn't want to be breaking down something while you're building something back up. And in fact, just to give you kind of a preview forward, catabolism and anabolism are often regulated, so controlled through the use of hormones. So I'm going to write here that hormones are a form of regulation and tell the body whether it should be in a catabolic or anabolic state.
ATP, or adenosine triphosphate, is often referred to as the currency of energy, or the energy store, adenosine, the energy store in biological systems. And what I want to do in this video is get a better appreciation of why that is. So adenosine triphosphate. So at first, this seems like a fairly complicated term, adenosine triphosphate. And even when we look at its molecular structure, it seems quite involved. But if we break it down to its constituent parts, it becomes a little bit more understandable, and we'll begin to appreciate how it is a store of energy in biological systems. So the first part is to break down this molecule between the part that is adenosine and the part that is the triphosphate, or the 3 phosphoryl groups. So the adenosine is this part of the molecule. Let me do it in that same color. So this part right over here is adenosine, and it's an adenine with connected to a ribose right over there. So that's the adenosine part. And then you have 3 phosphoryl groups, and when they break off, they can turn into a phosphate. And so the triphosphate part, triphosphate, you have 1 phosphoryl group, 2 phosphoryl groups, 2 phosphoryl groups, and 3 phosphoryl groups. So one way that you can conceptualize this molecule, which will make it a little bit easier to understand how it's a store of energy in biological systems, is to represent this whole adenosine group. Let's just represent that as an A. Actually, let's make it that an AD. And then let's just show it bonded to the 3 phosphoryl groups. So, and I'll make those with a P and a circle around it. So you can do it like that. Or sometimes you'll see it actually depicted, instead of just drawing these straight horizontal lines, you'll see it depicted with essentially higher energy bonds. So you'll see something like that to show that these bonds have a lot of energy. But I'll just do it this way for the sake of this video. But these are high energy bonds. Now, what does that mean? What does that mean that these are high energy bonds? It means that the electrons in this bond are in a high energy state. And if somehow this bond can be broken, these electrons are going to go into a more comfortable state, into a lower energy state. And as they go from a higher energy state into a lower, more comfortable energy state, they are going to release energy. One way to think about it is if I'm about to jump, if I'm in a plane and I'm about to jump out, I'm in a high energy state. I have a high potential energy. I just have to do a little thing and I'm going to fall down. And as I fall down, I can release energy. There will be friction with the air, or eventually when I guess hit the ground, that will release energy. I can compress a spring, or I can move a turbine, or who knows what I could do. But then when I'm sitting on my couch, then I'm at a low energy state. I'm comfortable. It's not obvious, how I could go to a lower energy state. I guess I could fall asleep or something like that. And these metaphors break down at some point. But that's one way to think about what's going on here. The electrons in this bond, if you can give them just the right circumstances, they can come out of that bond and go into a lower energy state and release energy. So one way to think about it, you start with ATP, adenosine triphosphate, and one possibility, you put it in the presence of water, and then hydrolysis will take place. And what you're going to end up with is one of these things are going to be essentially, one of these phosphoryl groups are going to be popped off and turn into a phosphate molecule. And so you're going to have then adenosine, since you don't have 3 phosphoryl groups anymore, you're going to that to take place. And what you're going to end up with is one of these things are going to be essentially, one of these phosphoryl groups are going to be popped off and turn into a phosphate molecule. And so you're going to have then adenosine, since you don't have 3 phosphoryl groups anymore, you're only going to have 2 phosphoryl groups. You're going to have adenosine diphosphate, often known as ADP. So let me write this down. This is ATP. This is ATP right over here, and this right over here is ADP, di for two phosphoryl groups, adenosine diphosphate, and then this one got plucked off. This one gets plucked off, or it pops off, and it's now bonded to the oxygen and one of the hydrogens from the water molecule, and then you could have another hydrogen proton. But the really important part of this I have not drawn yet. The really important part of it, as the electrons in this bond right over here go into a lower energy state, they are going to release energy. So plus energy. So here, this side of the reaction, energy released, and this side of the reaction, you see energy stored. And so as you study biochemistry, you will see time and time again energy being used in order to go from ADP and a phosphate to ADP. So that stores the energy. You'll see that in things like photosynthesis, where you use light energy to eventually get to a point where this P is put back on, using energy, putting this P back onto the ADP to get ATP. And then you'll see when biological systems need to use energy, that they'll use the ATP, and they'll essentially hydrolysis will take place, and they'll release that energy. Sometimes that energy could be used just to generate heat, and sometimes it can be used to actually forward some other reaction, or could change the conformation of a protein somehow. Whatever might be the case.
So let's talk about one of the most famous molecules in all of biochemistry, ATP. So why is ATP so famous? Well, it's the energy currency of the cell. And the reason it's called the energy currency of the cell is because it essentially fuels many life-sustaining reactions inside of our bodies. So some examples of these include biosynthesis of biomolecules. So remember, fats, proteins, carbohydrates, and nucleic acids are all essential to life, and building these molecules requires energy in the form of ATP. In addition, ATP is also used to contract our muscles, and this is very important in order to allow living organisms to move. And additionally, ATP is also involved in some ion movement across cell membranes. And of course, moving ions across membranes is really important to maintain a comfortable internal environment within the cell. Now, you could take my word for it that somehow ATP magically powers all of these life-sustaining processes, but you really don't have to. In fact, in this video, we're going to review some topics from general chemistry to really understand how ATP on a chemical level really fuels these reactions. Now, the topic we want to review in introductory chemistry is a thermodynamic parameter called Gibbs free energy, or as it's more often written as just simply delta G. So now recall that delta G is a quantitative number, and it's a number that's measured in units of joules, which is a measurement of energy. And depending on whether this value is positive or negative, it tells us whether or not a reaction requires energy or whether a reaction releases energy. Now remember that delta G is equal to the free energy of the products of a reaction minus the free energy of the reactants in a reaction. So if the change in Gibbs free energy is negative, which means that the products have a much smaller free energy than the reactants, we say that this reaction releases energy. On the other hand, if we have a positive value of delta G, which means that our products are at a much higher energy level than our reactants, we say that that reaction requires an input of energy. And I know we've been kind of nebulous about this term energy here, and so briefly I want to remind you that the change in free energy going from reactants to products of a reaction takes into account both the change in enthalpy as well as a change in entropy, which are two topics that you might be familiar with from general chemistry. So how does this all relate to ATP? Well, it turns out that there's a reaction involving ATP that has a very large negative delta G value. That is to say, it releases a lot of free energy. Specifically, this reaction involves ATP combining with water. And when it combines with water, we call this a hydrolysis reaction. So I'll just write that here to remind us. And the products of this reaction are a molecule called ADP and a free phosphate group. And like I mentioned before, the change in Gibbs free energy is very negative. So what's going on here? So ATP starts out with triphosphate, 3 phosphate groups, loses a phosphate group because it becomes diphosphate, and then it forms a free phosphate group that it cleaves off. So on first glance, it might seem that this reaction is not balanced because we don't have this hydrogen or oxygen on the right side of our equation. But I just want to note here that The negatively charged hydroxyl group becomes a part of the phosphate group, and the remaining hydrogen ion of the water combines with another molecule of water in solution to become a positively charged hydronium ion. And usually these two things are left out just for the sake of convenience, but I wanted to point them out here so that you wouldn't be confused by the stoichiometry. On the other hand, many biosynthesis reactions in the body have a positive delta G value. So remember, a positive delta G value means it requires an input of energy. And an example of this type of reaction is when we take a monomer, such as an amino acid, for example, and we string them together covalently to form a polymer. So in the case of an amino acid, that would mean we're forming a long peptide chain. Now here's where our knowledge of introductory chemistry comes in. So in thermodynamics, the study of energy changes, there's an important principle that states that the overall delta G for a reaction, I'm going to scroll down here to give us some more space. So the overall delta G for a reaction is equal to the sum of the delta G values for the individual steps of a reaction. So let's actually go ahead and add these two reactions together and see what happens. So let's write that out. So we have ATP as a reactant, as well as water, as well as our monomer subunits, and we are producing ADP, a free phosphate group, and a polymer. Now, what is the delta G for our overall reaction? Well, we just simply have to add the delta G values for each step. Now, I didn't give you, actual numerical values for each of these steps, but in general, the hydrolysis of ATP produces energy in excess of the energy needed for biosynthesis reactions, such as this one. So essentially what I'm saying is that if we add a very large negative number to a smaller positive number, we will get an overall negative delta G value. In other words, we have just taken a previously energetically unfavorable reaction with a positive delta G value and turned it into an energetically favorable reaction with a negative delta G value. And we have done this by what we call coupling a reaction that has a favorable delta G value, such as ATP hydrolysis, with a reaction that has an unfavorable delta G value. I want to mention that the ability to add these delta G values tells us nothing about the path that the reaction actually takes. And in fact, generally speaking, almost never does a reaction proceed in two discrete steps like it's written here. Instead, this coupled process often occurs simultaneously. But as you can see, it's still beneficial to separate these two reactions into two discrete steps so you can prove to yourself essentially why ATP with its negative delta G value is able to fuel energetically unfavorable processes. Oftentimes in biochemistry, we write energy requiring processes, such as in the conversion of a monomer to a larger polymer, as one-step reactions that are ultimately fueled by separate reaction involving the breakdown or hydrolysis. Remember, hydrolysis just means reaction with water of ATP to produce ADP and a free phosphate group. Now, when we write it this way, it implies that the breakdown of ATP is entirely separate from the biosynthesis reaction that it's fueling, when in fact, in the body, coupled reactions such as these often occur simultaneously. In fact, almost always, ATP is directly involved in the chemical reaction that it's fueling by directly donating or transferring one of its phosphate groups to the reaction it's involved in. And in this case, in our example, it donates a phosphate group directly to the monomer. To understand this mechanism even better, let's go ahead and take a look at a more tangible example in which we take a monomer and convert it into a polymer. So let's actually go ahead and take a look at building up nucleotides into a polynucleotide chain, such as DNA. So for the sake of simplicity, I'm going to go ahead and just draw a symbol for our nucleotide instead of writing out the entire chemical formula. But let's go ahead and review what the components of a nucleotide are. So remember that a nucleotide is composed of a sugar and a nitrogenous base, along with a phosphate group. And I'm going to highlight this phosphate group because it will be particularly important in the covalent bonds that form between nucleotides to form DNA. In addition, the sugars have a hydroxyl group that are also involved in these bonds. So I'm going to highlight that here as well. In the very first step of the reaction, two ATP molecules make an appearance, and specifically, they donate one phosphate group each to the phosphate group already on the nucleotide. Let's go ahead and draw out what our products look like. So we have our nucleotide and our untouched hydroxyl group, but now instead of one phosphate group, we have a total of 3 phosphate groups that are covalently bonded to one another. And because ATP gave up its phosphate group, we are left with 2 molecules of ADP. Now there's one point of confusion when we're talking about the breakdown of ATP into ADP. Many of us fall into this habit of saying that it's the breakdown of ATP into ADP that provides the energy for a reaction. But it turns out that this step of the reaction, in which we're essentially stacking up all these negatively charged phosphate groups that don't want to be next to each other, has a positive delta G value and cannot drive the reaction forward. But what does drive this overall reaction forward is the second step of the reaction. So let's talk about what happens in the second step. That are also involved. And specifically, they donate one phosphate group each to the phosphate group already on the nucleotide. Let's go ahead and draw out what are a total of 3 phosphate groups that are covalent of ADP action, in which we're essentially stacking up all these negatively charged phosphate groups that don't want to be next to each other, has a positive delta G value and cannot drive the reaction forward. But what does drive this overall reaction forward is the second step of the reaction. So let's talk about what happens in the second step. In the second step of the reaction, in comes a growing polynucleotide chain. So I'm going to go ahead and just draw 2 of these nucleotides. And remember that on one end of the growing polynucleotide chain is a hydroxyl group, which I'm highlighting in green. And on the other end is a phosphate group, which I'm highlighting in blue. The bonds between the nucleotides involve both the hydroxyl group in green and the phosphate group in blue. In this step of the reaction, the hydroxyl group of the growing polynucleotide chain essentially displaces the phosphate groups that were added in the previous step of the reaction. Now recall that this is possible because having 3 phosphate groups all crowded together like this makes the electrons in the bonds between the phosphate groups very energetically unstable. Think about all that negative charge that's close together that doesn't want to be. So let's go ahead and draw out what our final product looks like. And I'm going to go ahead and copy and paste this polynucleotide chain so we don't have to redraw all of it. So here it is. Go ahead and erase the parts that we don't need here. And now at the hydroxyl end, which is this green end right here, we have covalently bonded our new nucleotide. And so I'm just going to color code this by noting that the nucleotide with these stripes is the one that we're adding. And this covalent bond is between the hydroxyl group as well as the phosphate group, which I'm indicating here in blue. And the other hydroxyl group remains on the other end of the nucleotide, ready for another nucleotide to attach. Now let's not forget the paired phosphate group that was displaced in forming this covalent bond. This paired phosphate group, which has a name that you don't need to remember, it's called a pyrophosphate group, undergoes a hydrolysis reaction, that is, reaction with water to produce 2 independent phosphate groups. Now, the particular reaction mechanism isn't that relevant, but just so you know, the water essentially inserts itself asymmetrically in between these 2 phosphate groups and basically donates a hydroxyl group to one and a hydrogen to another. And because the split was asymmetric, these 2 phosphate groups still remain identical to one another. Now, the key point to take away here is that this reaction with water, this hydrolysis reaction, is very energetically favorable. Specifically, we say that it has a fairly large negative delta G value. And so it is this step of the reaction that ultimately drives this entire reaction forward. Now, if that doesn't fully click in your minds, let's also think about this from another perspective. Let's think about this from the perspective of equilibrium. So remember, there is a principle in chemistry called Le Chatelier's principle. And Le Chatelier's principle says that a system, such as a chemical reaction, will respond to a change in the system, such as a change in temperature or a change in concentrations of the reactants or products, by shifting in the direction that counters that change. So in this case, what is the change in our system? Well, the change in our system is that we are degrading our products. So remember, this phosphate group, this pyrophosphate group, is being broken down into individual phosphate groups. And so essentially what we're doing is we are removing the products of our reaction. And if we do this, the reaction will shift in the forward direction to produce more products. And the shift in the forward direction pushes this reaction forward. So ultimately, the reason I wanted to go through this mechanism with you was to really show you that ATP provides energy to a reaction by donating one of its phosphate groups or transferring one of its phosphate groups, and not through a simple hydrolysis reaction, even though that's often how it's written for convenience. Now, one question that I had about ATP hydrolysis when I was learning it was that if this overall reaction here, this coupled reaction, is energetically favorable, so this overall reaction has a negative delta G value, why doesn't ATP just donate its phosphate groups to any substrate in the body? Because ATP is floating around in an aqueous solution, so potentially it could donate its phosphate group to water and expend a lot of wasteful energy. The answer to this question involves reminding ourselves of the two factors that control whether or not a reaction will occur. So the first one is energetic. So is this reaction energetically favorable? And we usually look at the value of delta G. And in this case, our reaction is energetically favorable because delta G is less than 0. But the other factor that controls whether or not a reaction will occur is kinetics. And we usually talk about a parameter called the activation energy, which I'm going to abbreviate here as E sub A. And it turns out in this example, ATP has a very high activation energy. And I'm just going to skim the surface of this topic since our video is devoted just to this topic alone. But essentially, we say that this reaction is kinetically stable because it has a very high activation energy. And the way our body deals with this is that our body has enzymes that can lower the activation energy and allow the reaction to proceed when it should proceed. And so in our example, each step of the reaction has a specific enzyme that facilitates or catalyzes each step of the reaction. And this is actually very beneficial for the body because by having an energetically favorable but kinetically stable reaction, the body can selectively control whether or not energy will be used by controlling the enzymes that are available for the reaction to proceed. And so it's a very elegant system, and I hope that ultimately this entire video has given you a better picture of how ATP fuels energy requiring processes on a molecular level.
I want to do in this video is review what we learned from our chemistry classes about oxidation and the opposite of oxidation, reduction. And then see how what we learned in our chemistry class relates to the way that a biologist or biochemist might use these words, and hopefully we'll see that they're the same thing. So just as a bit of review, if you watch the chemistry playlist, oxidation, you can do it, and actually there's a famous mnemonic for it, oil rig, where the oil tells us that oxidation is losing, and I put it in quotes because you're not necessarily losing the electrons, I'll show you what I mean, is losing electrons, that you should have learned in your chemistry class. And then you also learned that reduction is gaining, I'll put that in quotes as well, is gaining electrons. And I put that in quotes because you're not necessarily gaining the electrons, you're more hogging it. And the reason why it's called reduction is because if you are gaining electrons, your notional charge, if you really were gaining them, would be reduced. The reason why this is called oxidizing is because you tend to lose electrons to oxygen. Although it doesn't have to be oxygen, it can be any molecule that will hog electrons. And I think a nice example is fair to kind of make this a little bit more concrete. Let's say I took some molecular hydrogen in a gaseous state, and I were to combust that with some molecular oxygen. This is what happened on the Hindenburg. You fill a balloon full of hydrogen and you get a little bit of spark, expose it to oxygen, and you're going to have a big explosion. But in the process, for every mole of molecular oxygen, if you have 2 moles of molecular hydrogen, I'm just making sure the equation is balanced, you're going to produce 2 moles of H2O plus a ton of heat. This thing is really going to blow. Plus a lot of heat. What I want to do, I mean, we can talk about the Hindenburg, but really the whole reason why I even wrote this is I want to show you what is getting oxidized and what is getting reduced. So in this situation right here, the hydrogen, molecular hydrogen, just looks like this. You have a hydrogen bond, with each sharing an electron with the other ones. They both can pretend that their 1s orbital is completely filled. So they're not losing electrons to each other. They're not hogging electrons one from the other. So we say that they have a neutral oxidative state. They haven't gained or lost electrons. They're just sharing them. The same thing is true for the molecular oxygen. Here, you actually have a double bond with 2 oxygens, but they're both oxygens. So there's no reason why one would gain or lose electrons from the other. When you go on this side of the equation, something interesting happens from the other. They're just sharing them. The same thing is true for the molecular oxygen. Here, you actually have a double bond with 2 oxygens, but they're both oxygens. So there's no reason why one would gain or lose electrons from the other. When you go on this side of the equation, something interesting happens. You have, for every oxygen, is connected to 2 hydrogens. And the way to think about it is that oxygen is hogging each of these hydrogens' electrons. So hydrogen has this 1 electron in the valence shell. You know, the deal with most covalent bonding is, hey, I give you an electron, you give me an electron, and we both have a complete pair. But we know, or hopefully we can review, that oxygen is much more electronegative than hydrogen. This is a little bit glucose reminiscent that is left over from our cellular respiration that you didn't think for now, but I'm actually going to connect all this in a future video. If you look at our periodic table, if you remember from the chemistry playlist, electronegativity increases as we go to the top right of the periodic table. These are the most electronegative. Elements. So over here, these are the least electronegative. And all electronegative means is likes to hog electrons. Let me write that. Electronegative just means likes to hog electrons. Hog electrons. So even though oxygen and hydrogen are in a covalent bond in water, they're sharing electrons. Oxygen is more electronegative, much more electronegative than hydrogen. So it's going to hog the electrons. But actually, if you take some elements on this side and you bond them with some guys over here, these are so much more electronegative than these left-hand elements. They'll actually completely steal the electron, not just hog it for most of the time. But when you talk about electronegativity, it just means likes the electrons. So when you look at this bond between hydrogen and oxygen, we saw from the periodic table, oxygen is a lot more electronegative. So the electrons spend a lot more time on oxygen. We learned about hydrogen bonding. We learned that it creates a partial negative charge on that side of the water molecule. It creates partial positive charges on this side. And the electrons still show up around the hydrogens every now and then. When you talk about oxidation and reduction, you say, look, there's no partial charge. If one guy is kind of hogging the electron more, for the sake of oxidation states, we're going to assume that he took the electron. So for an oxidation state, we'll assume that the oxygen in water takes the electron, and we'll give him an oxidation state of 1 minus, where the convention is you write the charge after the number for oxidation state, so you don't confuse it with actual charges. So this has a 1 minus because from an oxidation state point of view, you're saying it's taking the electron, it's gaining the electron. That's why I put it in quotes, because you're not really gaining it, you're just gaining it most of the time. You're hogging electrons. And likewise, this hydrogen, well, let me be careful, this isn't, he got 1 electron from this hydrogen, and he got another electron from this hydrogen. So instead of saying 1 minus, it should be 2 minus. It should be 2 minus, because he's hogging 1 electron from here and 1 electron from there. And in general, when oxygen is bonding with other non-oxygen atoms or non-oxygen elements, it tends to have a 2 minus or a negative 2 oxidation state. So this guy's 2 minus because he gained 2 electrons, right in quotes, gained 2 electrons. We know that he didn't gain them, that's just hogging them. These guys lost an electron each. So this guy's oxidation state is going to be 1 plus, and this guy's oxidation state is going to be 1 plus. So you could say, by combusting the hydrogen with the oxygen, that the hydrogens, before they had a 0 oxidation state, right? Each of these hydrogens had a 0 oxidation state. Now they have a 1 plus oxidation state because they lost their electrons when they bonded with the oxygen. So we say that these hydrogens have been oxidized. We say that the hydrogen has been oxidized. So due to this reaction, hydrogen has been oxidized. Why has it been oxidized? Because before it was able to share its electrons very nicely, but then it bonds with oxygen, which will hog its electrons. So the hydrogen is losing its electrons to the oxygen, so it's been oxidized. Similarly, the oxygen, due to this combustion reaction, due to this reaction right here, has been reduced. Has been reduced. Why has it been reduced? Here it was just sharing electrons; it wasn't losing or gaining it. But here, when it's bonded with an element with much lower electronegativity, all of a sudden it can start hogging the electrons. It gains electrons. So this hypothetical charge is reduced by 2. It's been reduced by, I can write that down, by 2. And if I wanted to actually account for all of the electrons, we're talking about losing electrons and gaining electrons. You can write 2 half reactions. This should all be a little bit of review from your chemistry class. It never hurts to see this again. I'm going to throw this in the biology playlist so that the biology people can hopefully refresh your memory with this stuff. But we can write 2 half reactions. We can say that we started off with 2 moles of molecular hydrogen. They have no oxidation state, or they're neutral, so I can write a 0 there if I want. And then I end up with, on the other side, I end up with 2 moles of H2. But each of the hydrogens now, each of the hydrogens have a +1 oxidation state. They each have a +1, it's 1 plus oxidation state. Or another way to think about it is each of these, there's 4 hydrogens here, right? This is molecular hydrogen has 2 hydrogens, and we have 2 moles of this. So there are 4 hydrogens here. Each of the 4 hydrogens lost an electron. So I could write this a +4 electrons. That's the half reaction for hydrogen. It lost 4 electrons, 4 electrons. That's the half reaction for hydrogen. It lost 4 electrons. So this is another way of saying that hydrogen, so I could write this a +4 electrons. That's the half reaction for hydrogen. It lost 4 electrons, so electrons. That's the half reaction for hydrogen. It lost 4 electrons, so this electrons. That's the half reaction. Hydrogen electrons, oil, oxidation is losing. And then the other half reaction, if I were to write the water, if I were to write the oxygen, so I'm starting with a mole of molecular oxygen, and I'm adding to that 4 electrons, right? I can't make electrons out of nowhere. I'm getting the electrons from the hydrogen, I'm adding to the oxygen. So the half reaction on this side, I end up with 2 moles, well, I can write it like this, 2 moles of oxygen, and each of them have an oxidation state of 2-. So these are the half reactions, and all this is showing is that the hydrogen, over the course of this combustion reaction, lost electrons, and that the oxygen gained the electrons that the hydrogen lost. So this tells us that oxygen is reduced. Now, this is all fair and good, and this is all a bit of a review of a chemistry class, but now I'm going to make things even more confusing because I'm going to introduce you to how a biologist thinks about it. So, and it's not always the case. Sometimes a biologist will use the definition you learned in your chemistry class, but a biologist, or many times in many biology textbooks, they'll say, and this used to confuse me to no end really, that oxidation is losing hydrogen atoms. And reduction is gaining hydrogen atoms. And at first when I exposed this, I was like, I've been in chemistry class, they talk about electrons, hydrogen atoms, it's a proton and an electron, how does it relate? And the reason why these 2 definitions, this is the whole point of this video, the reason why this definition is consistent with this one is because in the biological world, let me write this here, in the biological world, hydrogen is what tends to get swapped around, and it tends to bond with carbon, oxygen, phosphorus, nitrogen. And if we look at the periodic table, to bond, with carbon, oxygen, phosphorus, nitrogen. And if we look at the periodic table, we see where hydrogen is, and we see where carbon, nitrogen, oxygen and phosphorus and really all of this other stuff is, you see that all of the stuff that in biological systems hydrogen tends to bond with, the things it tends to bond with are much, much more electronegative. So if a carbon is bonding with a hydrogen, the carbon is hogging that electron. And then if that hydrogen gets transferred to an oxygen along with the electron, the carbon will lose, it lost the hydrogen atom, but it really lost the electron that it was hogging before. And now the oxygen can hog that electron. So these are really consistent definitions. And the whole reason why I showed you this example is because the biological definition kind of doesn't apply here. I mean, you could say, well, oxygen is definitely gaining hydrogens in this reaction. So we can definitely say that oxygen is being reduced still, according to the biological definition. But you can't really say that hydrogen is losing hydrogens here, right? In this situation, hydrogen is just losing electrons. It's not losing itself. I guess you could say it's losing itself as we take it over. But the biological definition just comes from the same notion that when hydrogen bonds with most things in biological compounds, it tends to give the electron. So if a carbon loses a hydrogen and gives it to an oxygen, the carbon will lose that hydrogen's electron that it wasn't able to hog. Now the oxygen is hogging it. So in biological compounds, it tends to give the electrons. So if a carbon loses a hydrogen and gives it to an oxygen, the carbon will lose that hydrogen's electron that it wasn't able to hog. Now the oxygen is hogging it. So the carbon would be oxidized and the oxygen would be reduced. Hope that doesn't confuse you. In the next video, I'll show you a couple more examples. And the whole reason why I'm doing this is to apply this to cellular respiration so that you don't get confused. Just when people say that, oh, the NAD is being reduced when it picks up the hydrogen, or it's being oxidized when it loses the hydrogen. And so forth and so on. I wanted to see that these are the same definition that you learned in your chemistry class.
I really want to go ahead and integrate some of the topics that you learned in general chemistry with topics in metabolism. Specifically, from a general chemistry perspective, I want to review electrochemistry. And then I'm going to connect it to one of the biggest topics in metabolism, the breakdown of glucose in a process called cellular respiration. And if you recall, cellular respiration describes the body's way of being able to efficiently produce the energy currency of the cell, which is ATP. Now, admittedly, this is kind of an unconventional way to first present the topic of cellular respiration, but what I think is really neat and what I think you'll realize is that we're really killing two birds with one stone here, because if you understand the concepts of electrochemistry, you also understand cellular respiration and vice versa. So let's go ahead and get started by returning to the topic of electrochemistry from general chemistry class. And let's go ahead and review a simple oxidation and reduction reaction between solid zinc and copper ions floating around in solution. So the AQ just stands for aqueous solution. And the products of this reaction are zinc ion and solid copper. Remember that whenever we're talking about reduction oxidation reactions, or as they're fondly referred to as redox reactions, we're talking about the flow of electrons. We must ask the question, what is gaining electrons and what's losing electrons? So copper here, which is positively charged, is gaining electrons and therefore being turned into solid copper, which has no charge. So we say it's gaining electrons, which means it's being reduced. On the other hand, solid zinc is turning into a positive charge. So it's losing negative charge. So we say here that it's losing electrons. It's being oxidized. And another way to really see the simultaneous gain and loss of electrons is to note here that there is a flow of electrons from the zinc, which is losing electrons, to the copper ions, which are then reduced to solid copper. And this, of course, is where electrochemistry comes in, because electrochemistry allows us to isolate this flow of electrons by building what is called an electrochemical cell. So let's go ahead and build an electrochemical cell for this particular reduction oxidation reaction. So I'm going to go ahead and draw two containers, which, if you recall, are referred to as half cells, because they're each half of the entire electrochemical cell. And remember that they're connected to one another through a wire that we can isolate the flow of electrons. And there's also another component called a salt bridge, which connects these two half cells. Just as a brief review, remember that this allows the flow of ions between each cell so that there's not a buildup of charge from this movement of electrons. Let's go ahead and remind ourselves where these electrons are coming from. So remember, the electrons are flowing from the zinc, which is losing electrons, to the copper, which is gaining electrons. And this is really the ingenious part of the electrochemical cell. It allows us to separate what's losing electrons, in this case solid zinc, from what's gaining electrons, which is the copper ions, and therefore allows us to isolate this flow of electrons through a wire. And of course, we also have zinc ions in solution on this side of the cell and solid copper. The take-home message is we're really separating what's getting oxidized from what's getting reduced. And ultimately, this flow of electrons through the wire, which is also referred to as current, allows us to perform energy-requiring processes such as in lighting up a light bulb. Now, here's the most important point that I want to make in this video. In oxidation on this electrons through a wire. And of course, we also have zinc ions in solution on this side of the cell and solid copper. The take-home message is we're really separating what's getting oxidized from what's getting reduced. And ultimately, this flow of electrons through the wire, which is also referred to as current, allows us to perform energy-requiring processes such as in lighting up a light bulb. Now, here's the most important point that I want to make in this video. In our body, we also isolate a flow of electrons during cellular respiration. But instead of lighting up a light bulb, we harness this flow of electrons to produce chemical energy in the form of ATP. So let's go ahead and take a look at how this works by looking at the overall reaction for cellular respiration. Specifically here, we're looking at the breakdown of glucose. So glucose is a chemical formula of 6 carbons, 12 hydrogens and 6 oxygens. And even though it's broken down in many multiple steps, the overall reaction for the breakdown of glucose is glucose combining with oxygen to produce water and carbon dioxide. And I'm going to go ahead and put in our stoichiometry here. This overall reaction is also a reduction oxidation process that involves a flow of electrons, just like our zinc and copper example. The flow of electrons, however, may not be as clear here. So I just want to take a minute and review kind of the oxidation and reduction from more of a biological perspective by looking at this reaction. So in the zinc and copper example, it was clear what was gaining and losing negative charge, but here we have to really think about electron density. And so when we look at this molecule of glucose, it is oxidized, that is, it loses electron density to form carbon dioxide. And the way we can rationalize it, so I'm going to go ahead and say that this is oxidized. If we look at the carbon, when it's attached to 2 atoms of oxygen, the oxygen atoms essentially steal the show because they are much more electronegative than the carbon. So carbon has very little electron density. It lost a lot of it from before when it was surrounded by hydrogens as well, which didn't steal the electrons as much. Now remember, if something's being oxidized, something must be reduced. In this case, our oxygen molecule, which is also referred to as kind of the final electron acceptor, is being reduced. It's gaining electron density. It's essentially gaining the electrons and the hydrogens that were lost from our glucose molecule. So here we have a gain of hydrogen and we form water. So water is the reduced product of the oxygen. Now, once again, we can summarize this flow of electrons by saying that the electrons flow from the glucose to the oxygen. So with this written out, I really want to go back to our electrochemical cell up here and point out that the solid zinc is really analogous to our glucose because both of these are losing electrons. And the copper ion here is really analogous to our oxygen because both of these are getting reduced. So I'm actually going to go ahead and erase the zinc and the copper and replace it with the glucose and the oxygen to essentially show you that there's kind of an analogy here between the electrochemical cell and cellular respiration. Now, clearly, I'm not being very technical about the creation of this electrochemical cell, mostly because, as you can guess, this really isn't what's happening in our body, but it's really this flow of electrons that our body harnesses. And instead of lighting up a light bulb here, which I'm going to erase here, instead of lighting up this light bulb, our body uses this flow of electrons. It harnesses it to allow the body to convert ADP back into ATP, which is, of course, the entire goal of cellular respiration, and ATP can fuel all of the energy requiring processes in our body. We can continue to extend this analogy between cellular respiration and the electrochemical cell we've drawn by pointing out that even though we don't have, a wire or separate containers in our body turns out that our body has actually functional equivalents of both of these two things. So let's start off with a wire. So in our body, instead of a wire, we have something called the electron transport chain, which I'm going to abbreviate here as ETC. And this electron transport chain contains an array of proteins that readily accept and lose electrons. Now, when it comes to having a functional equivalent for having separate abbreviate here as ETC. And this electron transport chain contains an array of proteins that readily accept and lose electrons. Now, when it comes to having a functional equivalent for having separate containers, our body is able to compartmentalize many of the reactions involved in cellular respiration. And specifically, I want to point out, you'll run into the fact that cellular respiration in its final step, which is called oxidative phosphorylation, occurs in the mitochondria. So I'm going to draw an organelle. It looks like a mitochondria. And the mitochondria has two kind of spaces because it has two membranes. It has the inside space as well as the outside space. And by having the oxidation and reduction reactions of cellular respiration occurring at different locations, so the interface between these two spaces and regulated by different proteins, allows the body to efficiently isolate the flow of electrons. So to summarize and to make one final point, I want to reiterate that glucose is broken down in a series of steps. And along the way, when it's oxidized, it forms various metabolites or byproducts that are more and more oxidized. And these metabolites essentially donate electrons at each step to molecules that are referred to as electron carrier molecules. And as a technicality, I want to point out that it's really these electron carrier molecules that ultimately donate electrons to the electron transport chain and ultimately to oxygen. So I'm going to go ahead and indicate this with an asterisk here and note that it's really the electron carrier molecules which directly donate electrons into this circuit.
Yep. I think so.
Normally, when we talk about the production of energy in the cell, glucose and ATP are the main characters of the story. But in this video, we're going to talk about a behind-the-scenes player called electron carrier molecules that really do play a vital role in this energy production process as well. But in order to talk about electron carrier molecules, we need to first review the main character of our story. So let's start off with glucose. So
All right, let's take a 10-minute. I need to pee. I need to pee. That's right. Don't do drugs. Don't study. So don't study. Don't study. Do drugs. MCAT.
Yeah. Yeah.
Yes, sir. Yes, sir. Yes, ma'am. Gotta get it done. Gotta get it done. I'm gonna get it done. Get it all done. I have to get it done. Have to get it done. Yup. Yup. I got some milk. Guys, check it out. I got some milk. Milk. Pretty cool, right? That's pretty good stuff. Ah, come on. What? You've got to be kidding me. No way. I'm gonna say it. Oh, maybe it's not this one. No. 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 Ah. What the heck? Huh. The heck? What happened to her? Oh, so rude. Nope. foods. Um, okay, hold on, guys. Be back.
Yup.
6 carbons, 12 hydrogens, and 6 oxygens, we know is broken down in our body to produce energy. And specifically, this breakdown process is an oxidation process, a process of losing electrons. And glucose is oxidized to carbon dioxide. And if the flow of electrons isn't very clear here to you, definitely review one of the previous videos on oxidation and reduction from a biological viewpoint. But the key idea is to notice that this carbon is far more oxidized or electron poor when it is attached to a highly electronegative oxygen molecule than when it's attached to hydrogen. So that's the key idea here. Now, in our bodies, this reaction does not take place in a single step. Instead, it takes in the behind-the-scene player called electron carrier molecules that really do play a vital role in this energy production process as well. But in order to talk about electron carrier molecules, we need to first review the main character of our story. So let's start off with glucose. So glucose, which has the chemical formula of 6 carbons, 12 hydrogens, and 6 oxygens, we know is broken down in our body to produce energy. And specifically, this breakdown process is an oxidation process, a process of losing electrons. And glucose is oxidized to carbon dioxide. And if the flow of electrons isn't very clear here to you, definitely review one of the previous videos on oxidation reduction from a biological viewpoint, but the key idea is to notice that this carbon is far more oxidized or electron poor when it is attached to highly electronegative oxygen molecule than when it's attached to hydrogen. So that's the key idea here. Now, in our bodies, this reaction does not take place in a single step. Instead, it takes place in many steps. And so I'm going to actually literally draw a staircase with many steps to indicate this. And I just want to note that this collective process of breaking down glucose in several steps is called cellular respiration, and that there are videos just devoted to the details of this process. All right, so now we're ready to talk about our electron carrier molecules. And we can think about our electron carrier molecules a bit like a molecular shuttle. I'm drawing a picture of an actual shuttle here just to remind us of this analogy. At each step of glucose's breakdown or oxidation, a new breakdown product of glucose is formed that is given a fancy name of a metabolite. And just for short, I'm going to abbreviate the rest of these as M. Now, the key point to realize here is that as glucose is broken down, the metabolites are more and more oxidized. That is to say, they have less electron density. And this is where our electron carriers come in. So recall that energy is extracted from this oxidation process by harnessing the flow of electrons. And it is the job of the electron carriers to harness the electrons that are lost at each step of the breakdown process. And so I'm going to go ahead and draw a metaphorical shuttle for our electron carrier molecule at each stage of glucose's breakdown. And these electron carrier molecules are, of course, carrying the electrons that are lost from the oxidation process. Ultimately, all of these electron carrier molecules are going to shuttle the electrons that are harnessed from the breakdown of glucose to something called the electron transport chain, which is in the mitochondria. And at this point, there are enzymes that can facilitate the transfer of these electrons to the final electron acceptor in our body, which is oxygen. And remember, it is this flow of electrons in the electron transport chain that allows the production of energy to produce ATP, the cell's currency of energy. So one question that you might have is, why does the body have such a complex mechanism that involves many steps and all of these electron carrier molecules to fuel the production of ATP? Well, let's reconsider the chemical equation that describes the overall breakdown of glucose. So glucose combines with oxygen to produce carbon dioxide and water. And just so that we conserve our mass, let's put in our stoichiometry. So this describes the overall breakdown of glucose, and we know that this reaction releases energy to fuel the production of ATP. Now, another way to view this process is as a simple combustion process, and combustion is exactly what it sounds like. It's what you think of when you think of something burning, and a combustion process just requires a fuel, and in this case, our carbon-rich or electron-rich molecule of glucose can be considered a fuel, And it also requires molecular oxygen, which we also have here. So to reword the question that I just posed, why doesn't glucose, the fuel, spontaneously combust in one step instead of being broken down in multiple steps inside our body? Let's first think about the consequences. It's required, but it sounds like it's what you think of when you think of something burning. And a combustion process just requires a fuel. And in this case, our carbon-rich or electron-rich molecule of glucose can be considered a fuel. And it also requires molecular oxygen, which we also have here. So to reword the question that I just posed, why doesn't glucose, the fuel, spontaneously combust in one step instead of being broken down in multiple steps inside our body?
What did she say?
Here. So to reword the question that I just posed, why doesn't glucose, the fuel, spontaneously combust in one step instead of being broken down in multiple steps inside our body? Let's first think about the consequences of combustion in our body. If glucose spontaneously combusted in our body to produce a large burst of energy, likely in the form of heat, all of that would be unusable energy, would be unusable, because remember, the only energy that our body really is able to use is in the form of ATP. And luckily for us, this combustion process does not take place in one step inside of our body, because even though it is energetically favorable, that is to say it releases energy, it is actually kinetically unfavorable, that is to say it has a very high activation energy. And you know this actually intuitively because the combustion or burning of sugar in food only happens when you overcook something at a high temperature. And a high temperature is able to overcome the activation energy to allow this combustion process to occur. Now, our bodies are, of course, at a temperature much lower than that needed for a combustion process, which is thankful because otherwise we would be producing all of this unusable energy. Instead, our body overcomes the high activation energy of this reaction by using enzymes at each step of the reaction. So I'm going to abbreviate this here as E. And there are two benefits of using a multitude of enzymes to break down glucose. So the first benefit, so I'm going to write benefit of enzymes. So the first benefit is that we're able to produce a large number of metabolites. And this is important because it allows our body to essentially reshuffle all of the metabolic products into many different pathways so that we can reuse and recycle these products as much as possible. And the second benefit of using many enzymes to break down glucose is that we have a slow and controlled oxidation of glucose, which allows us to harness all of that energy, which is in the form of the electrons that are being oxidized in a very controlled manner, as opposed to the big burst of heat that we would get in a single-step combustion process. And harness all of that energy, which is in the form of the electrons that are being oxidized in a very controlled manner, as opposed to the big burst of heat that we would get in a single-step combustion process. And electron carrier molecules play a big role in this controlled oxidation process that is facilitated by enzymes, as you can see in our diagram above, because they are essentially serving as a temporary storage for all of the electrons that are being lost by glucose. And in fact, because of their close association with the enzymes that facilitate the breakdown at each step, electron carriers are also called coenzymes. And coenzyme is exactly what it sounds like. It's a molecule or it's a chemical functional group that helps enzymes perform their function. Now, the enzymes involved in the breakdown of glucose, for the most part, are in the class of enzymes that have a special name called dehydrogenases. And these dehydrogenase enzymes do exactly what their name implies. They dehydrogenate the glucose. That is to say that they take away hydrogen. And when they're taking away hydrogen, they also take away electrons. And most often they do this by taking away 2 electrons along with a proton, which is what chemists call a hydrogenate the glucose. That is to say that they take away hydrogen. And when they're taking away hydrogen, they also take away electrons. And most often they do this by taking away 2 electrons along with a proton, which is what chemists call a hydride. And this hydride has a negative charge, so it's often referred to as a hydride ion. And, just another way to think of this is as one proton plus two electrons. Now, the two electron carrier molecules, or coenzymes, that are most commonly discussed in the breakdown of glucose are two molecules that go by the name of NAD and FAD. And I want to write down the reaction that occurs between these electron carrier molecules and the electrons that they're accepting from the glucose molecule through this dehydrogenase enzyme. So first, it's notable that NAD has a positive charge in its most oxidized form, while FAD does not. And each coenzyme reacts with two protons and two electrons each. In other words, reacting with a hydride ion plus an extra proton. And once the electron carrier molecules accept the electrons in this way, they become reduced. And the reduction products are slightly different for each. So in the case of NAD, it's reduced into NADH. So notice that we only have one hydrogen. And the reason for that is NAD can only accept one hydride ion. On the other hand, FAD can accept both hydrogens. So it's reduced to FADH2. The extra proton is just donated to solution in the case of NAD. And it is these molecules here, these reduced form of our electron carrier molecules, that shuttle the electrons to the electron transfer chain to allow for the production of ATP.
So in the previous video, we talked about how an ATP molecule can, in the presence of water, hydrolysis will take place, and one of the phosphoryl groups could be plunked off, and then how that would release energy because these electrons are going to be able to go into a lower energy state. That, they were kind of, one thing, there was uncomfortable. You could imagine that this was already kind of not that stable of a bond, that all of these these negative charges wanted to get it away from each other. And once this is plunked off, then of course, when they get into a more comfortable state, energy is released. But you might say, well, I want more. I want to actually see the mechanism by which the hydrolysis takes place. And so that's what I'm going to do in this video. So let's start with our ATP molecule, and let's throw some water in there, H2O. So let's say this is water right here, oxygen with two hydrogens, and I'll do the two pairs of oxygen that aren't in bonds right over here in the outermost shell. And actually, let me draw one more water molecule right over here. There's multiple ways that you could actually kind of depict this right over here. But let's say that one of these, let's say this water molecule right here, and obviously no organic, or actually no chemical reaction happens this cleanly. This is showing how it can happen if they just bump into each other in the exact right way. But this has got this pair of electrons. Let's say this pair of electrons is essentially given by this oxygen to this hydrogen proton. So we can draw it like this right there. So it nabs just the hydrogen. Then both of these electrons that are in this pair, that are in this bond, I should say, go back to the oxygen to form, essentially, you can think of this as a pair of electrons attached to the oxygen. And then that gives the oxygen license to allow these two electrons to form a bond with the phosphorus. Now, the phosphorus is in the mood to form 6 bonds. It's already got 5. And this is a fairly uncomfortable situation for it. So that allows these 2 electrons right over here to go, to this oxygen, or just like that. And so as a result of this, everything I've just depicted happening, what does it look like? Let me just draw a little arrow here. Well, now you're going to have your adenosine diphosphate. Let me put it over here. And just to be clear, this thing has now gained, so it was, this oxygen right over here was, one way you could think about it, it was party to a bond, so it was sharing 2 electrons. Now it's getting both of the electrons, so now it's going to have a negative charge. You could say it's, it had half of, actually had a little bit more than half, it's more electronegative than the phosphorus. But now it's going to get both of them. So now this is going to have a negative charge. This is the adenosine diphosphate. And now this phosphoryl group right over here, let me just redraw it. So it's going to look like this. So double bond to that oxygen. You have this oxygen right over here. So that's there. You have that oxygen right over there. And of course, the water molecule, or I guess now it's just going to be an OH group, is going to be, it has, let me see if I can make the colors interesting. So these two electrons have now formed a bond, and you have the oxygen and of course this hydrogen here. And I haven't drawn any of the other oxygens, but this thing still has two lone pairs. And of course, you have this character right over here who gained a proton. And so this one you can depict like this. So it's oxygen, hydrogen, hydrogen. It had one lone pair, but now it gave half of this lone pair to form a bond with that hydrogen. And hydrogen without an electron is just a proton. Actually, let me draw it like this, just so you can see it. So these two are now the two electrons in this bond with this hydrogen proton. So this right over here, this is a positively charged molecule right over here. And you could imagine, maybe this thing breaks off and it could be viewed as a proton, or you can view this as just a positive charged molecule. But either way, this is the reaction that we just depicted. You have ATP being a hydrolysis takes place. You're left with ADP. You're left with a released phosphate molecule. And then you're left with a positive charge. You could either view this as kind of a proton, or that proton attaches and forms a hydronium ion right over there. And of course, in the process of doing all of this, as these electrons got into a more comfortable situation, just sitting right over here and allowing this thing to break off, it releases energy. It releases energy, which is, in most biological systems, the whole point of having the ATP molecules around.
the ATP hydrolysis. ATP hydrolysis metabolism. Oh, shit, actually, that makes sense. Oh, actually, well, that's a good one. Yeah. It's most likely going to be somewhere. Let's see, let me think. Between 34 and 37. That's the or negative 11. Less than negative 11%. Oh, so Hold on. Why? ATP. Oh, 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 oh. Hold on, let me think. Who's going to be? Free energy. I would say free energy. Is it positive? Is it also positive? One more. I think it's gonna be less. Yeah, I think there's more. Not sure. I don't think it's true. Mhm. Thinking, creative atmosphere. Yeah, celebration. Um, and less than, um, Oh, okay. Why is it positive? And less than? I don't know if it's less than. I'm thinking D though. Yeah, okay. Oh, I'm not sure. They have its own about. I don't know. Free energy can never be negative. Where is it? What? Free energy system. Contains one more mono or one more phosphide hydrogen. Yeah, well, I was thinking it was delta G. If it was delta G, then I thought it'd be negative, but the last didn't make sense. I can't really find one that made sense, to be honest. The free energy reduced. This is true. Excuse me. Is there anything? Oh, okay, let's see. The absolute amount of energy in the system. Oh. Oh. Oh, got you. Shoot. Oh. Let me see. We're going to shift left. We're going to shift left. We shift left. Voltage is reactant side. Voltage is reactant side. Then, yeah, I believe that would make it spontaneous. This one. That makes sense. ATP concentrations are far below equilibrium. So the resurrection of spontaneous. The resurrection of spontaneous. So we know this is not necessarily plus with another reaction, so we need to change the energy, which is not this. So higher free energy, spontaneous. Spontaneous means it doesn't require energy. So that means that I don't actually. Spontaneous, right? Spontaneous. What the heck? All reactions require input into produce, so overcoming the activation energy. Oh. Let me see the graph again. Let's see. Can't say. So glucose is oxidized to let's say glucose is oxidized to carbon dioxide. 37 information. Carbon dioxide. water and carbon dioxide. Oh, okay, yeah. Oxygen is reduced to what molecule? It's reduced. Why? There's a flow of electric. This makes sense, right? It's the electrons are lost when glucose transferred over to electrons from glucose over to oxygen. Glucose and oxygen reactions. Glucose is oxidized to carbon dioxide, and oxygen is reduced to water. Oxygen is a fine electron acceptor. Oh, okay. So the electrons from glucose are transferred to oxygen, which is the form of this transfer. Actually, I would think it has a higher change, but it's unusable, right? Flow control. What? free energy is during the state of the system. System. I'm gonna do this. I thought it'd be unusable energy